Good morning to everyone. Welcome to UCI's KIT2. KIT2 stands for California Institute for Telecommunication and Information Technology. And my name is GP Lee, and GP stands for good person, easy to remember. Okay. And I'm currently directing this institute. And it is my great pleasure to welcome you to today's workshop. You may wonder, we can zoom in and out using all the remote way of doing the information exchange. Personally, I can tell you what I learned from zooming in and out in the last 3 years. Usually you sign into the meeting, you listen to what is the current events. After meeting, I don't remember who I talked to. I don't even know when I learned that topic. So the in-person meeting is so critical because there are perception of the information in time and space. And that is so crucial to the collaborations because that personal interaction really facilitate this kind of a teamwork needed for fighting the climate change. That's why I told my team, let's resume the in-person meeting. I know we still see people worry about maybe this is traffic, maybe there are virus and so on. But I think we have to go back. And this is how we innovate. By working together as a team, we can really change the world in a way to have a better life for everybody. So for today's program, what we are going to highlight are from the experts in the field, what they are currently working on to find the actionable solution to fight the climate change. And I want to take this opportunity to thank all the presenters and the distinguished presenter for sharing their information with us. And all the presentation material will be made available on our website. Also, I want to thank my staff for their diligent work, to put the workshop together, and recruiting the speakers and so on is not an easy way because I know everyone is so busy, especially right now. Our agenda in finding in delivering the solution by 2045 zero carbon emission society, that has a really urgency. And I know most of the speakers are so busy in coming up with a solution, put into the action plan. So ask them to really take time to come here to present their ideas. I think it's a very extraordinary ask. So I really want to thank them. And so now I would like to introduce the co-chair of the Calplug Advisory Board. We were supposed to have two co-chairs to present at the beginning of the workshop. And Doug just sent us a message yesterday. The flight got canceled still, and he need to be rerouted and won't come in until maybe afternoon. So he could not be here to present. So, and now I would like to invite the another co-chair, Kim, to come to the podium and to give us the latest. Thank you, Kim.
Test. Can you hear me? Chris? Okay, great. Excellent. I have some notes and I don't have any slides, so I'm just going to talk up here to you all. Welcome on behalf of the Calplug Advisory Board. I'm Dr. Kim Trenbeth. I'm the co-chair for the advisory board, and I want to welcome you on behalf of the entire board. So the board really sets the vision and the direction for Calplug, and it's implemented by the people who work here at Calplug. The board is made up of multiple people from different lines of work, including academia and research and industry and the utilities. So it's a really important group to move some of the solutions that we're all working on forward. So I've been on the board since 2019, and I've been the chair of the board since 2020, co-chair. I'm the innovation lead for systems technology, research and development at the National Renewable Energy Laboratory. That's also called NREL for short. We're a US Department of Energy national laboratory, so we conduct a lot of research for energy efficiency and renewable energy. And especially at NREL, we're really focused on those two things. And at NREL, I'm in the Building Sciences and Technology Center. I focus on a multitude of projects for commercial buildings research, and I manage a handful of projects there, but I really dive deep into plug and process loads research. So that's why I'm here as co-chair of the Calplug Advisory Board. And I think I want to say on behalf of Doug, he apologizes that he can't be here. So let's take a step back and think about our broad goal. Our broad goal is decarbonization to address climate change. And for US DOE, it's decarbonization, net zero carbon emissions by 2050. California is a little bit ahead of DOE, and I noticed that many years ago when I started working, or I started being involved with Calplug, that California is really taking the lead on decarbonization, which I think it's really great. And the rest of the country is now catching up, especially with defining the goals and identifying strategies to address these goals. So how do we get there? Well, first we need to work on including renewable energy into our portfolio. We're doing that now, but we need more renewable energy. And then also there's energy efficiency in our buildings. A big push is electrification so that we can take advantage of the renewable energy generation that's on the grid. And then in order to take advantage of electrification at the specific time that you want to be using power when renewable is on the grid, you need to have grid interactive efficient buildings. And finally, we want to make sure that we are transforming the buildings in a way that is affordable to all communities and provides resilience to all communities. This is called equitable decarbonization. So let's narrow it down to plug loads. And I'll use the word plug and process loads. A lot of times people say plug loads, some people say plug and process loads. The acronym for that is PPLs. Another acronym is MELS, which stands for miscellaneous electrical loads. So plug and process loads are any hardwired or plugged in electrical or gas load in your building that doesn't align with any other building end use. And those other building end uses are HVAC and lighting, for example. And if you want to talk about miscellaneous electric loads, then you remove the gas aspect of it. But plug and process loads, according to the EIA, take up 47% of whole building energy use, and this includes electric and gas. And that's a significant portion of the pie, and we're focusing a lot on HVAC and lighting, and we're making some great strides there. But plug and process loads take anywhere from plug-in devices that are like your smartphone for charging, all the way to bigger pieces of equipment like kitchen equipment and vertical transportation. So there are many different devices. This is a very multifaceted problem because there's not a one-size-fits-all solution. In addition, these devices are controlled by different building occupants in a building, especially in a commercial building. So if you want to implement a strategy, you have to get all the occupants in the building in line with that strategy and understanding what the energy efficiency goals are for the building. So we haven't made as many strides in this space, but I think that there's a great opportunity here. There's still time to define the pathway for achieving energy efficiency in plug and process loads or plug loads. And this is going to be done by research, industry, so developing the technologies and industry implementing the technologies. And then another factor that's going to become really true is the force of the market. Which way is the market going to push the implementation of the different technologies that are available, the different strategies that are available on the market today and in the future so that we can achieve PPL savings. So again, it's a multifaceted problem, but there's a multifaceted solution for this. And this solution, there's lots of solutions that the presenters are going to be talking about today in the room. We are going to use those solutions as building blocks to move everything forward. One solution might not be just the only thing. There's multiple solutions to solve this problem. When I started working on plug and process loads many years ago, there was still a lot of things that were undefined. We are moving forward from that point in time. We've made a lot of progress. For example, we've learned how to disaggregate loads. We've learned a little bit more about what's involved in a specific load, what's within that 47% that I was talking about earlier. We've developed many control technologies and we've tested them, and there are control technologies coming onto the market, such as smart outlets that are being offered by different companies. There's integration of these control technologies with other systems like lighting. There's many other, the pathways are still these things are being tested in field validations now, and what is successful is yet to be defined. So my point here is that we need to keep on working on this, in this space, on plug and process loads in order to continue our in order to continue our goal to achieve equitable decarbonization in the future. Now, I talk a lot about pathways and where we're going. Pathways, what I mean by pathways is there's different opportunities to achieve plug load savings, and what we're going to end up getting, what we are going to end up doing is really going to be defined by the research that we do and the uptake by the market. So what I see right now, based on our research that we've done at NREL, are 5 pathways to plug load decarbonization. And there's probably more, but I'll cover these really quickly. There's energy efficiency. There's also integrated control, interoperability, transferring the edge, the grid edge at buildings, and then finally, but most important, management and occupant strategies. So those 5 I will talk about a little bit now. So the first one is energy efficiency. Our current research has showed that there is a need to embed energy efficiency into the devices that we are producing and putting onto the market. So these can be anywhere from small electronic devices, all the way to medical imaging equipment. This has become apparent from work that we're doing with medical imaging equipment. We're looking at ways that we can make these pieces of equipment more energy efficient. And what people are expecting is that there's energy efficient inherently embedded in the device or the piece of equipment. But as research has shown, that's not always true. Calplug in the past has found that when you're pulling a product out of a box, sometimes it comes with a low power mode, but that low power mode is not enabled. So we want those products out of the box to have that low power mode enabled. So there's work to be done there. You can enable that low power mode out of the box, and also you can increase energy efficiency by putting energy efficiency into your design specifications of your anything from a small product like a cell phone or a lamp or a computer, all the way to these large pieces of equipment like escalators and medical imaging equipment. And when I say medical imaging equipment, I'm talking about MRIs, and they consume a lot of energy. They're very high power. Another thing that's a pathway in energy efficiency is implementing computer power management. There's third-party computer power management strategies on the market, and there's also computer power management embedded into some of the platforms that we use for computing today. And it's going to take working with the IT infrastructure, the IT folks to figure out strategies. And so now that we're talking about management strategies to achieve energy savings from better computer power management. I'll talk a little bit about integrated control. So what I mean by integrated control is a controller that not only controls one building end use, like lighting, but also controls the plug loads as well. So there's on the market right now, there are technologies that use the occupancy sensor to control your lighting as well as your plug loads. The challenge here is to make sure that these technologies are successful and there's a behavior aspect to it. You don't want to implement plug load control based on occupancy sensor for, say, a server that's in your room. That's not going to work. You're going to get a lot of occupant pushback. So there's some work to be done there. There's also field validations out there for plug load control embedded into the building automation system. So there's a lot of progress that's being made in this integrated control space. So I do expect products to be coming out on the market now and in the next few years that can be implemented into our buildings. A step beyond that is interoperability. Now, what I mean by interoperability is using similar languages and protocols for different types of devices from different manufacturers to be able to talk to each other. And we're starting to get some, I don't want to use the word grassroots because it's kind of grassroots. It's kind of a bottom-up approach. The device manufacturers have these smart IoT solutions. They're bringing them to market, but if they can't work together, it's going to cause a lot of stress to the market, and they're competing with each other as a result. If they make them interoperable, you could buy any type of smart speaker, and it could work with any kind of home energy management system. So we're seeing interoperability come as a push from the technology manufacturers, and hopefully we'll see that move from the residential space into the commercial space in the next 5 years. The next one is transforming the grid edge at buildings. Now what I mean by this is grid interactive buildings. Buildings that can control the load based on what kind of generation is on the grid at the time. So you want to be able to be consuming your power when the grid is producing renewables, and consuming or storing the power, we'll put it that way. And the grid interactive efficient buildings are going to allow for that. And putting plug loads involved with the GEB buildings, grid interactive efficient buildings, or the acronym GIB, will allow you to control more of that load and help us achieve decarbonization. And then also, your devices could respond to grid signals. So as devices get more and more smart and grid signals get more and more advanced, a piece of equipment could respond directly to the signal from the utility. So that's something that we're looking forward to happening in the future. And then the most important thing, I think, is this engagement of these management strategies that engage the occupant. It has been proven that if you don't have these management strategies, your technologies to control plug loads are not going to be successful. For example, if you want to deploy something such as smart outlets to control your load, you need to deploy a management strategy to communicate what these outlets are doing in your building so that your occupants understand what's going on. Another example is working with technologies such as automatic receptacle controls that are already in building code, how to get more uptake and use of them in buildings instead of having people daisy chain guys, I'm so sorry. What am I looking for? Power strips, sorry. Instead of daisy chaining power strips to the one uncontrolled outlet, you want people to effectively use the controlled outlet. And so what NREL is doing is we're working with the NEMA task force for automatic receptacle controls. And there's other national labs working on this as well, PNNL, Pacific Northwest National Lab in particular. And what we're doing is saying, hey, building occupants expect a common device, a common symbol when they look at a receptacle outlet. So showing which one is controlled using similar markings might be an effective way to achieving some of this uptake. And when we are achieving this uptake, what I mean is that there's opportunity of 30% PPL energy savings from the technologies that are existing in the market today and the control strategies that are well known today. It's a matter of implementing them into your buildings. So those are the pathways, again, energy efficiency, integrated control, interoperability, grid interactive efficient buildings, and management and occupant engagement strategies. So what if we don't move forward with these strategies. What if it's business as usual, where you're not going to be taking advantage of the potential to save 30% energy efficiency, and you're not going to be achieving decarbonization because PPLs, plug and process loads, are 47% of whole building energy use. There's a lot of low-hanging fruits, such as having the building be on in the middle of the night when there's nobody in it. So there's a lot of places where we can capture some of these energy savings really quickly if we continue to work towards these different pathways for achieving those savings. At Calplug, we are addressing this problem. We are working to solutions in this space. And Calplug, through this workshop and other engagements, brings together people from academia, research, utilities, and industry to come together to think about this problem and solve it. Calplug is the premier institution for plug load research in the United States. So what I'm saying here is I hope that we continue to fund these areas of interesting research to continue to produce building blocks that will generate the pathway for decarbonization in plug loads. So during this workshop, we're going to hear a lot about various things related to PPLs. So first, we're going to hear from Calplug and the research that's being done. We're going to have a presentation on how we're reducing energy use in manufacturing through the SMART IIC, the Industrial Assessment Center. We're also going to hear about how we are researching energy use in different pieces of different devices and equipment through the Pledix project. Then we'll hear about electrification in the portfolio and where the United States is going with electrification. We'll have speakers on tackling the problem through controls. So there's different control strategies, different control technologies, and we'll learn about that. And then finally, we're going to talk about specific energy efficient devices and appliances. So thank you all for being here. When you're here, I hope that you take advantage of being here. We're all working in the plug load space, so let's talk in between presentations. Take the time to learn during the presentations and think about how the information that you learn in the presentations can be applied to the solutions that you're working on in your building, in your business, in your technology development. And finally, I want to say that this is a really exciting area to be working in. There's a lot of push for HVAC and lighting. We're achieving lots of accomplishments there. But this area is a nuanced area that is great to be in right now because, again, we're defining those solution pathways right now. So it's great to be starting in this spot, working in this spot, and watching those solutions emerge from all the great work that we're doing. So again, welcome. Thank you for being here. And I look forward to hearing your presentations and talking to you later today.
So now I would like to invite the first speaker, Katie. So Katie is going to present some of the activity in Calplug. And as Kim just mentioned, what we're working on. So Katie, please.
Went to the end. Sorry.
Sorry.
Thank you.
Sorry.
No worries. Good morning, everyone. My name is Katie Gladdick, and I'm the project manager at Calplug. And today, I will be talking a little bit about our current project, which is called PLETIX, Plug Load Energy Testing for Informing Codes and Standards. This is a project that's funded by the California Energy Commission. And right now, we are sort of in the middle of our testing phase, where we're just starting to test the devices that were included in this project. So I don't have a lot of data for you yet, but what I do have is a policy background. So like, what are the questions that CEC is interested in that are spurring this new focus on developing codes and standards for some new areas? So just a quick overview of this project. It's to assess the opportunities for new California codes and standards for products that are not currently included in state energy efficiency regulations. So these are the Titles 20 and 24, and is focused mainly on 3 device categories, which are imaging devices, residential networking equipment, and laboratory equipment. So it's kind of a mixed bag, different kinds of questions to be raised here about these different kinds of devices and how they operate and what kind of modes could be implemented to save more energy. So just a little bit of background about our team. The prime research team is the California Energy Alliance, and they are primarily a policy organization in the state. Calplug is looking at the commercial imaging devices, and then we have teams at CSUN looking at the commercial laboratory equipment, and at UC Davis and the Lighting Technology Center looking at the residential networking equipment. So sort of the 30,000-foot view, why are plug load codes and standards important? So this is a great segue from what Kim was just saying. That, yeah, we have this situation where plug and process loads are making up 47% of commercial building and use energy. And this is going to only increase over the next few years. By 2040, that is going to be almost half of the commercial energy equipment. And that's partly because HVAC and lighting end uses have already been pretty much taken care of in terms of their energy efficiency, ability to meet new standards for energy efficiency. So the next big area to look at are these plug-in process loads that are making up quite a lot, but at the individual level, they only use a little bit of energy, so they're more difficult to look at. And so one of the main policy tools that we have is to implement codes and standards. I'm going to talk a little bit about some research that was recently released by the International Energy Agency. And this is the first sort of longitudinal study of how successful these programs have been over the past 20 or so years. And so it's some really interesting data that sort of confirms what we've all been suspecting, that these programs work. So energy efficiency standards and labeling programs, or EESLs, are in 2 different categories. So there's the minimum energy performance standards. Those are things that are regulated by law, so your energy agency laws, your California Title 20, those are, you know, the specific requirements that is necessary. The other thing that's included in these EESLs are energy labels. So that would be any kind of regulatory requirement for showing what the energy intensity of that product is, and we'll look at an example later of that. So these programs currently operate in more than 120 countries worldwide and cover over 100 different appliance and equipment categories across the residential, commercial, and industrial sectors. And in the advanced programs that have been around for a long time, you can save up to 15% of the country's annual total electricity consumption, which is quite significant. So just looking at these graphs here, you can see that the US and the European Union already have quite advanced programs, and they've been around for at least 20 years. And China is also catching up, even though they haven't been around quite as long. So it just shows you that when you have like very large industrial economy, you can quite quickly realize some of these savings. Just to give you a little bit more context here, EESLs also help spur energy efficiency in emerging technology. You can see that this graph here shows the savings of the different categories over time. So this is in 1 year, you can get up to 8 or 9% of new product energy consumption, energy saving realizations. And this is particularly the case in the electronics sector, as you can see, and that's one of the sectors that Calplug particularly focuses on. And over a longer time, you can save actually up to 50% of the emerging technology requirements. And so this is one of the reasons that the policy is so important, because it's a major driver of helping the manufacturing sector to improve their energy efficiency when they design their programs. So just looking a little bit more particularly close to home at the US policy context, at the federal level, you have regulations such as the energy agency that makes all the regulations about what actually is required for these different categories. And then you have things like voluntary agreements or Energy Star, and those sort of set forward the testing standards that become pretty routine in terms of what is a standardization that is required for different product categories. And then at the state level, you have state regulations. For example, in California, you have Title 20 and some of the Senate bills and Assembly bills that make up the policy drivers. And then you have the utilities that, I'm not going to talk about that as much today, but that's also a really important part of the whole energy savings economy in terms of developing rebate programs and incentive programs at the municipal or the IOU level. So looking a little bit more at the US federal codes and standards, we have the DOE federal appliance standards. And we have another interesting thing, which is the Federal Trade Commission appliance labeling rule, which requires these little yellow code regulations to be in all on products such as refrigerators, freezers, dishwashers, clothes washers, water heaters, furnaces, boilers, central air conditioners, heat pumps, and pool heaters. And this gives you all the information that you need to do a comparison across the different types of products that you might want to purchase in terms of how much energy you can save. And there's also a label that's optional whether the product has opted into the Energy Star program. And as Kim was also mentioning, California has one of the more advanced codes and standard programs in the country. The overall driver of this is the Senate Bill 100, which is the California Renewable Standard. And this sets out a plan for 100% of total retail sales of electricity in California to come from renewable energy sources and zero carbon resources by 2045. So it's not just about generating solar and wind power, but it's also about how can we electrify our buildings to make this transition more attainable. And the main policy that sets forth the standards for appliances in California is Title 20, and it goes much further beyond the federal codes in terms of the kinds of products that are covered. So as you can see, there are products such as televisions, disc players, compact audio products, and desktop computers, which have mandatory requirements in terms of power usage and standby readiness, which goes beyond what the federal legislation requires, and it also helps to drive the industry to develop products that have these settings and that meet these requirements. So I'm just going to talk a little bit about what we've done so far in Pledix in terms of codes and standards or research. Looking at the imaging equipment, there are several current codes and standards that cover this sector, such as the main one that is the primary test procedure and product specification is the Energy Star requirement, and that is a voluntary agreement at this point. There hasn't been any codes and standards for codifying that into law yet. Other things are the EPEAT residential, the EPEAT standard, which is also a label that is for printers, that specifies not just energy efficiency requirements, but also looks a little bit at the environmental impact requirements, which is going to be a new thing coming up soon in terms of GHG reductions and in terms of particulate matter, particularly from ink sources. There's the Blue Angel eco-label, which is one of the main drivers of policy in the European Union. And then there's the standby and low power mode requirement under IEC 62301, which is something that we're looking at in terms of how we can integrate our testing procedure with the Energy Star procedure and sort of make the case for better standby requirements. And another interesting thing to note about imaging equipment is there was recently, up until last year, there was a standard, or a voluntary agreement rather, in the European Union, and that was taken off the table recently because the European Commission decided that their new the new label that they put forward was not sufficient enough to meet their aggressive energy reduction goals. So that's now going into a code and standard through the Energy Commission, through the European Commission. And so rather than a voluntary agreement in Europe, they'll have a mandatory code and standard. That hasn't been passed yet, but we're definitely keeping our eyes on that because that will be sort of the first in the world example of this, and that will help to inform California's policy as well. Then looking at the residential networking equipment, there are several voluntary agreements. The main one is the voluntary agreement of SNE, which is signed on to by all of the major manufacturers. And then there's the Code of Conduct in Europe, which is the sister program to that in Europe. And then finally, looking at the laboratory equipment, there aren't very many Energy Star requirements at all yet. This is pretty much a blue ocean category in general. The only one that exists is the specification for lab freezers and refrigerators. And there's another ongoing effort through My Green Lab to develop a standard for, or a label for autoclaves, but that hasn't been developed to publication yet. And this is an interesting category because, as Kim was stating before with medical equipment, this is very similar. There's, the energy and water usage is very intense in devices such as autoclaves and centrifuges. And there's definitely a need to take a look at what kinds of new modes we can implement to save some of that energy. So just taking a little look at what our next plans are in the Pledix project. Right now, we are finalizing our test approaches and methodologies, and this is going to be based mainly on starting with the existing solutions, such as the Energy Star program test methodologies, looking at best-in-class devices and features that are on the market currently. Another important factor, also to echo Kim, is looking at how we can implement better power management and low power modes in these devices, testing real-world conditions to see how low power modes actually work in not in just laboratory settings, but in real-world conditions, and getting a better sense of what kinds of requirements we might want to suggest to CEC for labeling. We're also going to take a look at some of the usage issues, so designing user interfaces for efficient device operation and reducing wasteful usage patterns, and a general discovery mode approach where we will see what other kinds of interesting results come from our testing methodology. So the step that we're in now is device procurement and testing, and we expect this to run through July and August of this year, and hopefully we will have some interesting results by the next time that we meet in the fall. And the final stage would be to analyze our results, estimate energy savings, and make our final recommendations to the Energy Commission, and that should be between this end of this year and early next year. So takeaways, plug loads are becoming a larger portion of commercial and residential building loads as our other end uses such as HVAC and lighting are addressed for EE already. Energy efficiency standard and labeling programs are a great solution for this. They've been proven effective internationally, both saving energy and reducing carbon emissions, and spurring new energy efficiency measures in emerging technologies. We have our federal and California standards as templates to continue to improve energy efficiency through our closing standards. And there are many new opportunities for new categories, such as addressing issues like low power modes, and encouraging industry to continue making energy efficiency improvements for new technologies. So thank you very much, and let me know if you have any questions.
Hey there. It
Hi.
seemed like a lot of what we discussed or what you discussed was on the standard side rather than the code side. Are you looking at building codes that might benefit PPLs as well?
Sure. So building codes are going to be more California Title 24 and ASHRAE 90.1. So those are certainly important for things like controlled outlets, and in the case of laboratory equipment, looking at how wired equipment gets implemented through the water maintenance and things like that. But it's not exactly so much of an issue right now for some of the other smaller devices. Yeah.
Hi, good presentation. Thank
Thank you.
you very much. A question, are you working with any manufacturers of these equipment, or maybe like the CTA, the Consumers Technology Association, or something like that?
Yeah, that's a great question. Yes, we've had, so the CEC requires us to have a technology council to take a look at what we've been doing and just sort of give their feedback. So we have CTA, we have Doug on our board, and we also have a number of other stakeholders from printer manufacturers and the residential networking and laboratory distributors who are helping us out on that as well. So yeah.
I was curious about your selection of the medical devices, imaging devices, home networking, and lab equipment, because when I think about energy efficiency, I think electric motors use a lot of energy. You know, there's heat dispensement, you know, and then cooling the building to offset the heat. You know, so I think about a selection criteria that focuses on the components that generate the most amount of electricity, the greatest amount of load within a component, right? So a fan or the IC. So I'm curious why you selected these three areas and what other areas are of interest or that would have been, you know, also in the selection criteria.
Yeah, that's great. So this was part of a mandate from the CEC. We were given several different kinds of categories that they were interested in, and these three were the selection that we made. There were no motors that were offered in this program. What I will say is that we are also looking at some of the component, we're gonna try to break down the energy usage for different components of the products that we're testing, and we would definitely want to make some recommendations regarding things like motors. Certainly for some of the lab equipment, they use things that could be made into via variable frequency drives, more efficient ways of saving energy through better motor technology. So it's a secondary kind of thing that we're looking at, but for this project, that wasn't the mandate.
Again, thank you for the presentation, and maybe channeling Doug, because he's not here right now. So clearly there's been progress made in standards and codes, but hasn't been kind of a substantial portion of the gains also been made by the voluntary things that industry are doing. So I do hope that one of the portions of the recommendations say if a voluntary method is working, that should actually be recognized. So especially because I work in residential network equipment, I mean, that would be great if we can continue to make sure that, especially in these innovations that occur probably every 2 years, you know,
Yeah.
it's like Wi-Fi, you know, from Wi-Fi 4, 5, 6, 7, 8, right? And so it would be very hard to track those kinds of things. And with Wi-Fi 7, we're making a huge change for multiple links, right? And it's not because we want to waste energy, it's because people are demanding low latency and those kinds of problems. So when possible, I think let's also make sure that we acknowledge the work that has been done with voluntary agreements and to continue to keep that in order to keep the innovation that we all desire to be effectively being available to everyone as well too. So.
Yes, that's a great point, and we are keeping it pretty agnostic in terms of our testing methods. So if it turns out that the best method is an Energy Star method or the residential network voluntary agreement, then that's the recommendation that we would make.
Any other questions? If not, let's thank Katie again.
Thank you.
Now it's my pleasure to introduce Chelsea, and she is program manager for Industrial Assessment Center, which focus on the energy efficiency assessment for manufacturers.
mess it up.
You have yours up already?
Yeah.
Oh, go ahead and hit it up. I was waiting for that.
Okay. Well, thank you, GP, and thank you all for being here. Welcome to the Calplug Workshop. My name is Chelsea Chowdhury. I'm the program manager for the Smart IAC, and I'm very excited to provide some updates on what the IAC program has been up to for the past year. So just in case anyone's unfamiliar, we are the Smart IAC, and that stands for the Sustainable Manufacturing Alliance for Research and Training Industrial Assessment Center. We are part of the U.S. Department of Energy's Industrial Assessment Center program. So we will go to different clients, small and medium-sized enterprises, and provide free energy consulting services, as well as that's providing good hands-on training for our students at the same time. So the typical Department of Energy assessment focuses on energy efficiency, waste reduction, and productivity enhancements. So in terms of energy efficiency, we can go and look at pretty much anything at a client's site, like their process or some pieces of equipment, their building envelope, and we can try to find energy saving recommendations that we can make, try to save them on their energy as well as save on their utility costs. So just some examples when we're on a client's site, we can look at lighting, air compressors, motors, HVAC, the list goes on and on. So there are so many different opportunities that we are going to look at to try to find energy saving opportunities. We are also trying to bring the SMART into our IAC by incorporating some more advanced topics such as smart manufacturing, cybersecurity, life cycle analysis, and fuel switching, to try to bring some of these more innovative recommendations when we're on our client's site. We'll be looking for these opportunities as well. Okay, and then just an idea of what our typical energy assessments look like. So we will go, our team will go to the client's site. We'll take a tour of their manufacturing facility. And that's a good chance for students to start taking notes, especially about their different their process or different equipment they might have, and it's a good time to start thinking of ideas for energy savings. After that, we could then have a team brainstorming session where the students can start to share their ideas, and we can really start to develop a game plan for what we want to focus on. After that, we could go and take some more data collection on the shop floor, whether that be installing data loggers onto a piece of equipment to either track its usage or its energy consumption for a couple weeks, or we could go out and take live measurements of temperatures or air pressures, lighting levels, or collecting nameplate information. So we'll go back out and make sure we collect whatever information we want for our report. After that, we would then start working on the report, which is, it goes through the full engineering and economic analysis. So we really want to show step by step the calculations where the energy savings and then the cost savings are coming from for our clients. And then 6 to 9 months after that, we'd follow up just to see how well the report worked for them and if they were able to implement any of our ideas. We are just now starting this phase with our initial clients. So we don't quite have the data yet, but just anecdotally, I was chatting with one of our clients. That report, we looked at their compressed air leaks in their compressed air system. So we brought our ultrasonic leak detector and scanned their area, trying to identify leaks for them. Another big one that we recommended was they had a natural gas boiler, and we recommended they switch that to electric. Of course, trying to push electrification as much as we can. So I was emailing him, and he came back that they actually went out and bought their own leak detection equipment so they could start a regular maintenance program from our recommendation, which was great, as well as he's getting quotes for a new electric boiler, so they're seriously moving forward with that project as well. So that was great to see. Okay, and then just some quick stats for you. We have 24 students in our training program. Our students are really great. I'm a little biased, but no, we have some really hardworking and really smart students on our team. So that definitely, makes the whole program go forward. We have completed 16 assessments so far. That has been 11 industrial assessments and 5 commercial assessments. And I will kind of dig into the data from that a little bit later, as well as we've created 5 reports finalized from those assessments that this data can be pulled from. All right, and then just looking a little bit more into our student team, a little bit later we'll invite a few of them to come up and share some updates and some of their experiences as well, so stay tuned for that. So we are spread out across UCI, CSUN, and Cypress campuses. As you can see at the bottom left there, we have a nice mix of graduate students as well as seniors, juniors, and sophomores. So we see that having that blend of experience levels to our team has been very beneficial. Some of the more experienced students will take more of the leadership roles and be mentors for some of the newer students. So that's definitely great to see. And then we have about half of our team is mechanical engineering, and the other half is kind of sprinkled across various other engineering disciplines. We've also found that to be very beneficial, that it's not just the mechanical engineering viewpoint. We also have, the chemies and the electrical engineers, the materials. We have those different viewpoints to bring into our recommendations. All right, and like I said, we did 11 industrial assessments. We had a couple that were metal finishing, and a couple that were electronics recycling companies. Otherwise, we had a nice range of aerospace, door locks, beverage packaging, electronics, filters, defense, and flooring. For the commercial building side, we've done a few community centers, as well as a retail location, a commercial launderer, and education building. So as you can see, we kind of also been seeing a wide variety of different industries that we've gone to, which is also great for the students to get to experience a variety of things. All right, and just to kind of cover the types of recommendations we've been seeing so far, the top ones have been compressed air and lighting. We've also looked at some building envelope improvements, as well as eliminate natural gas. Like I said earlier, we are trying to push towards electrification whenever we can. Otherwise, we've done a few process heat improvements, some demand reduction strategies. Solar, of course, that's another big one for California, and then motors and controls. And just to highlight a few of the top recommendations we've seen so far, reducing the compressed air leaks is big. If we can, install a storage tank and then optimize their whole compressed air system, we could ideally reduce the air pressure. Lighting is pretty straightforward. If we could get some LEDs as well as some controls to control the lights. We love recommending heat pump water heaters, so that's one of my personal favorites, is that technology has advanced so much lately. And then eliminate natural gas, of course, if we can get rid of either propane forklifts or any natural gas boilers, ovens, furnaces. That's definitely something we want to try to focus on. For process heat, if there's a way to either recover the waste heat and reuse it or reduce the heat that's being lost. And then for demand reduction, if we could shift any of their processes off peak, that would be ideal. Energy generation, of course, we look a lot into solar, either on their rooftop or separate parking structures, as well as storage. And then high efficiency motors or variable speed drives. And then looking at how that all translates into energy savings that we've seen so far from our 5 reports. You can see in the second column there is the energy savings that we're proposing if they implement all of our recommendations compared to what their total energy usage was. We can kind of see where the energy savings are coming from. And then how that translates into cost savings. Of course, that depends on a lot of factors, like their utility rate structure and the time of use and demand charges and all that good stuff. But we can see here how those recommendations could translate into energy cost savings. Okay, and now I kind of wanted to highlight the Student Research Award that IAC was awarded last year. So we were awarded one of 8 research awards, and these are sponsored by the U.S. Department of Energy. These are really designed to create funding for some assessment-inspired research projects. So we have submitted our proposal on mixing hydrogen with natural gas as a way for decarbonization. And up next, we'd like to invite the student lead, Daniela Ruins, up. Daniela is a PhD student in the Aerospace and Mechanical Engineering Department. She joined our team already having a very strong background in energy after her bachelor's degree working in industry, designing solar systems, before coming back to UCI and working on other hydrogen-related projects that made her a really perfect fit for our team here. So please join me in welcoming Daniela.
Thank you, Chelsea, for that introduction. And yeah, I'm going to talk a little bit about this research project that we have related to hydrogen. So I'm going to try to give you like the big picture to make it easier to understand the problem and what we are doing. But if in the meantime you have any questions, let me know. So with the industrial sector growing in the US, we also have an increase in the energy demand. Basically, this means that we have a higher greenhouse gas emissions, right? So to give you an idea on that, in 2020, 24% of the US greenhouse gas emissions came from the industrial sector. And in 2021, 38% of the total energy final use came from the sector. We also know that the greenhouse gas emission forecast is expected to increase as it was determined by the U.S. Information Administration, and you can see the projection over here. We are expecting these emissions to increase. So because of all of those things, the U.S. Department of Energy has decided to release a decarbonization map, as it was mentioned earlier. They have different paths that we can follow in order to reduce those greenhouse gas emissions, but there's one specifically that focuses on the use of low carbon fuels, feedstocks, and energy sources, such as hydrogen. As Chelsea was mentioning, we also focus on the fuel switching, right? So that's why this was a good match with our project. So hydrogen has been drawing a lot of attention because its properties, such as high energy density, that it can work in a very wide range of operating temperatures, going from ambient to 1,000 degrees C, that it has a high performance, and of course, its ability to reduce the greenhouse gas emissions. And right now, hydrogen, it's not ready to be used to solve our short-term problems because it needs to be produced. So the cost of production for hydrogen can compete yet with hydrocarbons, and it's also hard to store. But as an alternative, we have proposed, it has been proposed, the hydrogen blending. This basically means, as this diagram over here indicates, blending hydrogen in our current natural gas pipeline in a way to reduce these greenhouse gas emissions. So as part of what we do, we visit at the IAC Center, we visit different industries where we have identified a couple of clients that might be able to, might be good candidates to install or implement this hydrogen blending project. So what we are proposing to study that feasibility is pretty much a modeling study where considering the real processes, the real operating conditions, and the real infrastructure, how feasible it is to implement this hydrogen blending. And we are planning to also include an economical analysis to actually cover all the knots that might lead into a real implementation for these clients. And as part of what we want to deliver on the project, of course, a paper, when you work doing research, those are great, we love those. And a poster and a video that might help us to deliver this information to all kind of public to make sure everyone knows what we are doing without the need to be like a specialized reader. So basically, that's what we are working right now on the simulation part, and we are working very, very hard to make this happen before our deadline. So if someone has any questions, I'll be happy to take those.
Oh, okay. Yeah. On this, once again, great presentations from both of you. Thank you very much. Um, on this particular hydrogen project, what is the maximum amount of hydrogen that can be mixed? Have you done any work related to that without affecting the quality of the pipe or the pipeline or whatever?
Thank you. That's a great question. So right now we're only focusing on simulation, but of course there has been a lot of experimental work done, and it has been established so far that around 30% of hydrogen blending is still safe without actually needing to modify a lot of the infrastructure of the natural gas pipeline. So right now that's our limit, and we're going down from there to see what's the perfect combination, not perfect, but the ideal combination considering their specific operating conditions and infrastructure for each client to determine what percentage of hydrogen will be the ideal case for them.
Thank you. Question for Chelsea. Chelsea, you showed, I think 5 companies or 5 industries examples of how much they could save energy based on your assessments. Has anyone done anything, subsequently in the sense that any of the companies implemented any? And if they have not, do you have plans to verify it after the implementation?
Yeah, we usually will follow up 6 to 9 months after the assessment. So we are just reaching that phase for our initial clients. So we don't have the formal data yet. We should be getting that pretty soon. They'll start trickling in as we're 6 to 9 months out from the assessment. So we will start seeing that data soon. Hopefully we'll get a lot of clients that are implementing our ideas. So far we've seen a lot of interest from our clients, so I'm very optimistic about the real world implementation.
Do you want to mention about the incentive program from DOE?
Oh yeah. And one thing we are definitely promoting when we're on our assessments is that the Department of Energy, they've been expanding the IAC program a lot recently with some of the funding that has gone through. One thing they are going to be offering is implementation grants to help with some of these bigger projects, especially the very capital intensive projects can get hard to actually implement. So the DOE is going to help with up to $300,000 grants, one-to-one matching for the clients. So if they have a IAC assessment done or one of the other DOE partnership assessments done, they could then apply for one of these grants and get some assistance in their funding.
Yeah, I just had a quick question about the hydrogen mixing too. I mean, there are pressure issues, right, between the gases. So does the existing infrastructure handle that, or is this running new pipeline from the hydrogen generation to the customer?
Thank you. Great question too. So yes, there is one of the main focuses of this hydrogen blending is a pressure drop because natural gas and hydrogen have different energy densities, so that means a pressure drop. So we are considering that until the point they have to do minimum infrastructure investment, they can still use what they have and still inject that hydrogen into their pipeline. So that's why we have set 30% of hydrogen as our limit and going down from there, considering that we need to increase the amount of fuel we have in order to still deliver the same power that they have, only considering natural gas.
And my question is to Chelsea. A number of times you mentioned your enthusiasm for switching out natural gas for electric appliances. I'm looking at a chart right now that says that currently SCE renewable portfolio is about 35% of their energy production. So another 65% is still coming from, I would assume, natural gas plants. So where's the math to support replacing gas appliances or gas devices in manufacturing with electrical if Edison's just going to take that 65%, then have to have transmission to the point. So I'm just curious whether or not there's actually a GHG reduction at this point until Edison gets to a higher percentage of renewable. Thank you.
Yeah, no, very good question. Especially we like to sell it more as if they're going to also do solar for their site, that switching out to as much electrical equipment as they can would really be just extra beneficial. So that's really what we're trying to sell it as. We obviously want SCE to continue to be making improvements and moving towards more renewable energy. So that is still a bit of a headache for us, I guess, but we are trying to promote it more as that if you're also going to do solar or do some other renewable projects yourself on site, that it would make it way more beneficial.
Maybe I can make a comment. I think it's when we perform the assessment in manufacturer side, when we look at electrification of their process load, we also consider availability of the solar energy generated locally. And I can give you one example. Some of the company we visit, they do a lot of electroplating. Right? So this is a very, very generic industrial process for coating purpose, right? And what is electroplating? The voltage is only 5 volts. Lots of currents, DC current, DC voltage. And currently, what do? You get 208 volts and then convert to DC. And you know how much efficiency lost. So what if you have your solar panels directly using that DC voltage, DC current for electroplating? A lot of energy saving, efficiency gain, and reduce the production cost. And that's the product. I encourage you to develop the product. Right? So I think it's the IEC really open up opportunity to find out what are the innovation needed in the new markets. That's how the students really get excited. I'm just giving you one example. When I visit Japan, when I mention that idea, everyone say, wow, that's a great idea. They pay so much money for electricity. Right? So that's why I'm saying is, think about, we don't need to limit with what existing infrastructure we have at hand. Think outside the box. This is we are in the innovative economy. This is why we are so great, right? Competing with other countries because we are innovative. So that is my message to all of you. Think outside the box. Okay. Any other questions?
Can I just ask my question?
I've got the mic first, if you don't. Sorry. On one of the assessments, I noticed there was a lot of things that were suggested. One of them I thought was carbon dioxide sensing, I couldn't quite figure out how that was fit into the whole pieces. Thank you.
Yeah, no, that's a really good question, actually. So that was more of a unique recommendation that we were looking at. It was for commercial buildings, so it was mixed use space that there's the CO2 levels that are required for buildings. In that specific retail location, we could, have a specific level. They weren't monitoring that, so they just had their HVAC, the ventilation open, the air dampers open all the time instead of, they could monitor the CO2 emissions. If the levels are lower, they could close those dampers, save a little bit of energy. So using that CO2 sensor to open and close the dampers to reduce their energy is what we were looking at for that one.
Thank you. Excellent presentations. Thank you so much. A couple questions, and they're detail-oriented. There was leak detection by one client as well as replacing the boiler with an electric one. What are the costs for those two? So there was 2 purchases. There was one to identify their leaks on their own. How much did that cost the company, and was that financially feasible?
Yeah, Yeah, it kind of depends on what type of equipment they purchase. You know, ours was about 3,700. So if they make that initial investment, but the recommendation for air leaks was about 15,000 a year. So just investing that maybe 4,000 once to save 15,000 each year continuously, it really makes sense for them.
Oh, that's great. And then, are you, this is a general IAC question, are you able to collaborate with other IACs and learn best practices from them?
Yeah, absolutely. We have been in touch with a few other IACs working on some best practices, but we are also working on other collaborations as well with IAC centers, so definitely.
And then final question is, what are the sizes of the manufacturing facilities in the buildings that you are evaluating? I think you had a slide on that, but I missed it.
You mean like square footage?
Square footage.
Yeah. For industrial, there's not really a requirement to determine the size of the company. We really more look at the number of employees, the amount of sales, their energy costs, and if they already have a professional energy engineer dedicated to doing that as their job. If they don't have that resource available, that's when we could come into these what we would consider small and medium sized based on their employees, their sales, that kind of thing.
Do you know those numbers off the top of your head?
Yeah, it has to be less than 500 employees. Utility energy bills need to be between 100,000 and 2.5 million. Sales need to be less than 250 million annually. And then within 150 miles of either UCI or CSUN, this geographical area.
Oh, great. That's great.
Yeah.
And thanks, Chelsea. Great presentation. Daniela, congratulations on the team award, your award for the work and the research that you've done. Is this a all industrial assessment center awards? You're competing against all the other industrial assessment center students across the nation?
Yes, it is for the IAC program, so the other 38 or so universities can compete as well. So the fact that we are one of 8 was really great.
Yeah, that's amazing. Congratulations on that award. That's great work. Thank you.
Yeah, well, I will, we had one more quick, this will be very, very quick, student testimonial, just to share some of their experiences. We'd like to invite Jeannie Lang down. She's a senior in biomedical engineering here at UCI, and she'll be pursuing her PhD in the fall, which is amazing. She kind of joined our program very early, almost right from the beginning, and has been an integral part of both assessments and helping out the team. So we were very excited. Please join me in welcoming Jeannie.
Thank you, Chelsea. Hi everyone. So for the past year, I've had the fortunate opportunity to go on several assessments with the IAC. Through these assessments, I've learned a lot about different manufacturing types of manufacturing, from metal cutting, printing circuit boards, and even making carpets. I also have become more mindful of plant layouts, as the best way to maximize efficiency is to have a good plant layout and have a good workflow. So all these things I've never thought about before, especially as a biomedical engineer. So I'll definitely keep that in mind for my future studies in manufacturing. So the IAC has been a very rewarding experience for me, and I believe for all the students that have gone on these assessments. Now, even at home and just day-to-day life, I become more mindful, thinking about saving energy, just anywhere I can. So thank you, Chelsea and Dr. Lee, for helping us students on the assessments, and thank you. Great.
Okay. I'll jump the gun on questions, but if there's anything else, please let me know. Do we have one more quick?
Thank you for the presentation. How are the clients selected?
Oh yeah, they could reach out to us, or we could also reach out to them. So far, we've had a lot of clients reaching out to us, trying to get signed up for this program, which is great that the word is getting out there. We're pushing our marketing materials out, and then clients are reaching out to us to set up these assessments.
Or you can introduce some company interested
Yeah.
in taking assessment.
Yes, definitely send them our way.
Quick question just regarding what you've encountered out there, seeing the diversity of plants and so forth. What is your experience in robotics in the industries that you have sort of encountered, and what sort of trends or what kind of reception have you seen from manufacturers of maybe adopting those sorts of automated processes and replacing perhaps human intervention?
Yeah.
And how are you viewing that overall in the IAC?
Yeah, that's a great question. We have seen it somewhat, definitely not in all the places we've been to, but some of the places are upgrading their equipment. Like we had an automatic inspection machine instead of manual inspection, so that was kind of interesting, as well as some smaller robotic cells set up. It's definitely not as much as I would have thought, so I think in the future that will keep coming and keep coming. But we have been seeing bits and pieces here and there, and if there's a way that we can find, especially productivity enhancements through that kind of technology, that's something we would look into for our report.
Yeah, I have a follow-up question to that. That's a great question about robotics. Why do you think there's not as much robotics in the manufacturing facilities compared to what you would have thought?
Yeah, I mean, I think a lot of it is the capital intensity of a lot of those projects, as well as we've seen a lot of cybersecurity concerns when we're on site that they don't want to be connecting. Especially, we want to recommend IoT sensors and smart manufacturing setups, but there is some pushback on cybersecurity concerns integrating that into their system. But we are finding solutions to a lot of that. So
maybe I can jump in to answer that. Because IAC performing the assessment specifically for SMM and small and medium manufacturers. Small means less than 50 employee in the company. Medium is less than 500, right? So that is the range of the company we are dealing with. And what is the key asset in SMM is the people. That's what we noticed first, because they have been working with people as their family members. And it's a very hard decision for the owner to displace their family members. So the adoption rate is slow compared to the large size corporations. And second thing is we notice they are still not digitizing their manufacturing floor. Lack of visibility of how the facility run and how to run the facility in efficient way. I think that is the area we do see the innovation can come in to help them to really think about leveraging the meaning and value of the data to improve deeper efficiencies. I think that is right away they see something they can do, but how to get onto that digitization as compared to Industry 4.0 promoted by Germany, we are behind, be honest, right? You look at Germany, 67% of the company already implement Industry 4.0. In US, very, very low. That's something we have to do. I think it's once you get to that level and the automation with a robot will come in, because you need to have the infrastructure in place to really leverage those automated systems like robots. I think we are more or less in the last 20 years, we hollow our manufacturing workforce in the United States. Right? We outsourcing majority of the job. To come back, and we also notice they have a hard time to recruit skillful workforce. Right? All the company we visit, they contact Chelsea, say, do you have a student graduate? Do you have a student to do intern? And I look at one survey right now in US, 89% of the company could not hire skillful workforce. That is the challenge we are facing. Our hope is through this kind of activity, we can motivate students to get back to the manufacturing, our core values. And manufacturing is no longer like a traditional thinking of a blue-collar job. It's the newer generation cyber manufacturing and introducing data, introducing robots, and a lot of innovation will come out. Right? I think that is the hope to inspire our students and to go into that field.
Thanks, GP. This is really interesting. I see manufacturing as one of the pathways to achieving some of the the energy efficient technologies, zero carbon technologies that we will be placing into buildings. And if we can manufacture them in the US, it's going to be a little bit more streamlined to accomplish that. So I think there's a lot of synergies between what the IAC is doing as well with what Calplug is, the whole big picture all together. So I think that's great.
Thank you.
Yes.
All right, thank you. Good morning, everybody, and thank you very much for the opportunity to be here. I really appreciate this invitation and also the warm welcome that I've received from this whole group. My name is Caitlin Murphy, and I'm also with NREL, the same institution that Kim introduced earlier in the workshop today. The first thing you need to do to fix a problem is to admit you have one. So I will start by saying that I'm one of the people who takes plug loads and we put them into the other category. And then we do our modeling without really thinking about all the details and opportunities that are available within plug loads. And you'll see that in the slides in the presentation today. That's partially just based on, this is not sort of our usual audience for the study that we performed a few years ago now. But it was also to highlight the areas where I think it would be really nice to try to get some more collaboration and some more opportunities leveraged to figure out what can these large and growing loads do as we're trying to approach this decarbonization problem. And in my work, that's typically from sort of the grid perspective, so planning and operating the electric power system, especially the bulk power system, thinking about how we can work together to try to reduce the challenges and reduce the size of the problem that we're trying to tackle all at once. So the study I'll be presenting on is the Electrification Futures Study. This is a multi-year study that was funded under the Obama administration, continued into the following administration, and finished up just a couple of years ago. So the study evolved a lot over time as we were sort of initially scoping it and then executing the work. But we always set out to answer these sort of 5 crucial questions. So the first question is, how might electrification influence electricity demand and use patterns? We were focused on the big categories that Kim mentioned early on in the presentation. So we're really focused on what happens as you fuel switch your heating and cooling systems, your water heaters, for example, your washers, your dryers, things like that, mostly in residential and commercial buildings, but also in the transportation sector. So we wanted to understand not just how much would overall demand change, but also the shape of that demand, because that really influences how we plan the bulk power system and the generation and transmission assets that we need to meet those demands. So that's the next piece, which is really the capacity of the bulk power system. How would that need to transform to meet those changing demands? And as we start to replace our fossil fuel generation with renewable assets and with storage, how does that impact the operations of the systems, and can we still operate the system reliably? That's the third question that we set out to answer. The fourth piece kind of ties into all the first three, and it's really focused on flexibility, both in electricity supply and in electricity demand. What sources of flexibility offer the greatest value to the energy system as a whole, and which ones make the biggest difference when we're planning and operating that system in terms of making sure things remain reliable and affordable? And then finally, what are sort of the broader impacts of this entire transition? So looking across the entire energy chain, not the entire energy supply chain, but load to generation and how you operate the system, all your fuel use. What does that mean in terms of the costs, the benefits, and other impacts such as greenhouse gas emissions and also air quality impacts associated with this energy transition? So this is the entire scope of the 3-year study that has been completed. All of our results are published. All of our data actually is also publicly available. I'll just pull out a few of the key pieces here that I thought were most relevant for this audience, and especially for sort of seeding future opportunities for collaboration in this space. So first, just to define the scope and what we mean when we say electrification. In this study, what we were talking about was the shift from any non-electric source of energy to electricity at the point of final consumption. So we're not talking about the production of hydrogen to then decarbonize through the use of clean hydrogen, for example. We're not talking about new loads that could be used to help shift other emissions-intensive industries, such as urban agriculture, for example. We're really just looking at this fuel switching question. And that's what's highlighted in this figure on the right. So the entire square or rectangle represents about 3/4 of primary energy use in 2015. Everything above the line is direct fuel use, and it was direct fuel use in 2015. Everything below it is already electrified. So these last two columns are our buildings, and we see that a lot of the demand in buildings is already served by electricity. So the opportunity in that space is just inherently less overall in terms of what it means for evolving the energy system and decarbonizing it through a pathway of electrification. There are still really important aspects here. You'll see the other category at the top. That would be where some of the gas loads, for example, would live. But ultimately, a lot of this is already electrified. It's already incorporated into our electricity planning tools because we're already looking at the load shapes that are on the system today. In transportation, though, we have almost the entire sector available to us as an opportunity for electrification. And industry in that red column there, that's a little bit of a mixed bag. There's a lot of opportunity, but at the same time, not all of those demands lend themselves to electrification. This study is not out there saying we're going to electrify everything. We're really looking for the electrification opportunities that make sense from the entire energy system perspective. So you'll see that there's very little movement in industry in the study that we have here, and that's because we looked at it, we considered it, and ultimately we didn't see the argument for all of the opportunities. There were some key areas where there are process improvements that could be achieved through electrification. We did look at those, but we didn't go out and try to electrify all of the thermal heating requirements, for example, the steam requirements in industry. Okay, so just walking through a few of the key findings on the load side of things, so thinking about the electricity demand. This is really designed to show the flow of how it worked. We have a really detailed equipment and stock turnover model. So what we tried to do is look at a snapshot of the equipment today, think about how long each of those equipment pieces tends to last before someone replaces it, and then we applied different levels of sales shares for electric versus non-electric technologies. So we're also not asking customers to throw out their perfectly good water heater or their perfectly good furnace or car. We're waiting for that replacement, and then we're seeing in that year, what do we assume to be the available sales share of electric equipment in that case, and then we sort of turn over all of the equipment. So to the question before about, does it make sense to electrify today from an emissions perspective, I think a really important piece of that question is thinking about how often we replace this equipment. If it doesn't make sense today, but it would make sense in 5 years based on the grid mix, you don't want to wait to replace it today because it might be 20 years before you're buying that equipment again. So we can't just look at today's grid mix when we're thinking about emissions impacts of electrification. We have to think about the lifetime of that equipment and where we think the grid is going based on all the different commitments and policy requirements that we have in place. So with those sales shares, that really evolves our stock over time. We have different levels of aggressiveness in terms of how much we think folks will be adopting electric equipment and how that varies by equipment type. So there was a comment made earlier that lighting and HVAC equipment, for example, that's already lending itself really well to beneficial decarbonization through electrification. we expect higher sales shares in those areas because they are cost effective. Same with light duty vehicles, for example. Other areas we might see that it really doesn't make sense until we get to sort of a high electrification future that's driven by a variety of factors, not just the cost argument for the customer, for example. So that's the 3 columns here. The one you can't see is called reference because I think in today's picture, we just don't think that's a realistic reference anymore. With the Inflation Reduction Act and the change and all of the incentives that are available for electric equipment, we don't see that as a reasonable future going forwards. Not to say we think medium is what the future is going to be, but we don't really want to think about what we think of as sort of a counterfactual based on the policy and the incentives in the system today. So what I'll focus on today are the medium and high electrification levels. Medium we tend to describe as sort of taking advantage of the low-hanging fruits. So those measures that actually are cost-effective from the customer perspective, ignoring things like hurdle rates and range anxiety, for example, but thinking about from the pure cost of buying and operating the equipment, does it make sense to switch? That's what's focused on in medium. And then in high electrification, that would require significant drivers that are moving beyond what's available today from incentives and from the cost argument on its own. So just a couple of highlights by sector. Transportation is where we see the most opportunity from the sort of the grid planning perspective, just thinking about the total load that could be added to the system and what we would need to plan for when we're building generation and transmission assets. This again is because there's almost no electricity use in that sector at all, but also because there's a lot of energy use there that lends itself to electrification. So these warm shades are kind of the emergence of the electric vehicle options within each transportation sector. So light duty cars and trucks, lots of opportunity there. You guys, in Colorado, we sometimes have to say this to sort of remind people electric cars are out there, although there's plenty of electric cars out there too. But probably don't need to tell you guys about electric cars and their availability. But we do see sort of those sectors blowing up with electric cars, both in terms of plug-in hybrid and full electric vehicles. We also see some more muted, but also noticeable opportunities within medium-duty vehicles and also within transit buses. Again, just thinking about kind of the economic argument in those cases. Heavy-duty vehicles, we're not really sure, at least at the time of this study, that it was there in terms of battery electric vehicles being an option for some of the short-range applications, for example. But in the high scenario, we start to get more aggressive and look at what could this mean, again, so that we're making sure the grid is planning for a future and not getting caught without thinking about pretty huge amounts of load that could be entering the system and that needs to be met reliably and affordably. So this is just another way of looking at what I said in terms of the transportation sector being the biggest opportunity, the biggest thing to plan for from a capacity perspective on the bulk power system. So on the left side of the chart on the left is the historical electricity demand and how it's grown over time, with that plateau in the last couple decades, just representing the fact that efficiency has sort of been keeping pace with any electricity demand growth that has been happening. This growing blue wedge then is what we see happening as more and more electric vehicles enter the system. So it's returning us to the growth rates that we had in the early parts of the system, nothing like what we've seen in the last couple decades. Almost entirely based on the adoption of vehicles, and this is again partially because buildings are already so heavily electrified. And as we replace some of our less efficient electric equipment with more efficient electric equipment, they tend to offset each other as well. So the building wedges are pretty small in this chart. What changes more noticeably, though, is the size and the timing of the peak demand, and this is actually what the bulk power system is planning for. So this is an area I'd be really interested in talking to more folks about on the plug load side of things, is understanding what the opportunity is to avoid these peak periods. When I think about escalators and other forms of vertical transportation, I don't see a lot of opportunity for flexibility, for example, but maybe there are some other aspects of plug loads that could be leveraged in a way to help respond to signals from the grid when these types of events are happening on the charging side of things to try to mitigate the stress on the grid, mitigate the amount of resources that are needed. So that's an area I'd really be interested in chatting with folks about if they have ideas in that area. So looking more at building sort of fuel switching opportunities, we do see a significant impact from the adoption of electric space and water heating. It didn't show up clearly in that annual demand chart on the previous slide for all the reasons that I already mentioned, but it does show up more prominently when we're thinking about peak demand. These charts on the right here are just showing sort of the evolution and the trade-off, sorry about that, as we go from direct fuel use to electric, and what that means in terms of the total share of services provided by electricity in our different scenarios. This is mostly to give a sense of how how aggressive we're being in these scenarios. And again, that we're not necessarily electrifying everything, but trying to electrify the things that would make sense. We do have included in our studies some of the services that I think would fall under plug loads, which would be things like electric cooking, for example. Not a huge share of total building load, but in commercial buildings it can be, of certain applications, it can be a more sizable load, and it is included in both our fuel switching opportunities and our flexible load assumptions in our modeling. So this is, again, just another way to look at the impact of heating, especially space heating, on peak demand periods. So the left-hand chart is a snapshot in 2015. The size of each pie is how big the peak demand is in that state. And then the different colors represent the timing of that peak demand, looking at the top 100 hours. So lots of red and orange pie charts on the left-hand side. This is showing summer and kind of early fall peaking periods, which is what California would fall under, for example. The size of the pie varies strongly based on mostly population, but also sort of the sources of industry and things like that within a given state. There's only a few regions sort of in today's world that are showing a little bit of winter peaking, and that's just based on the location of that system, mostly the climate, for example. When we look at 2050 in our simulations, now looking at our high electrification scenario, so lots of EVs, lots of heat pumps in our buildings, we start to see the emergence, especially in the eastern part of the United States, of a dual peaking period or even strongly winter peaking periods. And this is that air source heat pump load coming into play and taking over, layered with your EV loads, which are actually year-round. So in this case, what we're seeing is the whole pie gets bigger, mostly because of the EVs, and then you start to shift into winter peaking for regions where there's a lot of heating demand that can be very peaky and can make for the highest 100 hours actually falling almost entirely during your winter season, especially in the eastern United States. And of course, this drives the need for additional capacity, generation capacity, and also additional transmission to move the generation from our really high quality resource regions into the demand centers, for example. So what we see in a lot of our scenarios is a large build out of wind in the middle of the country. But of course, the loads tend to be on the coasts and in Texas, for example. And so in that case, what we need to do is expand our transmission lines to try to bring that wind resource to our newly electrified loads. In all of our results, we have these available on the website, but this is just meant to show a snapshot of the actual generation mix varies by region, just based on what the lowest cost resources are there and their alignment with the timing of those loads. And then also taking into account the cost of trying to build and expand those transmission lines. So the previous chart maybe oversimplified this, so I just wanted to have one more example of how much of a step change this is from our current system. So again, on the left side is the historical build out of the entire bulk power system from its evolution to today. So originally, a lot of hydropower. We added a lot of coal resources. The 70s and 80s saw large additions of nuclear power, which of course have very high capacity factors. The 2000s saw the explosion of natural gas with the fracking revolution and the emergence of low-cost gas in the United States. More recently, we've seen a lot of new wind and solar resources, but still relatively small compared to the size of the overall system. What we're talking about in our simulations on the right side is an explosion of wind and solar. And this is not a decarbonized future, this is just a business as usual future. So just accommodating those new loads requires, not this exact resource mix, but this magnitude of capacity addition to meet those loads. And if we wanted it to be entirely decarbonized, we have to take all of this gas and replace it with more renewables, which have lower capacity factors, makes the chart even bigger. So this is a huge problem, and this is why we're planning for it. And this is why we want to take advantage of all the sources of flexibility that we can to try to avoid adding capacity that we don't need on the bulk power system if there are lower cost sources of flexibility that can help us move those loads out of peak periods and into times when we have an abundance of renewables that could be used for something beneficial. So for the most part, when we talk about this, we focus on electric vehicles. That's mostly because vehicles charge for a long time. They park for a long time. So there's a lot of opportunity there to, as long as your charging needs are met within that 12-hour period while it's parked, the customer's not going to notice a degradation of their service. The grid's going to notice it a lot if we don't have all of those cars starting to charge at the exact same time in their level 2 or level 3 chargers, or thinking about medium heavy duty vehicles, even bigger chargers. So there's a lot of benefits that have been already studied at the distribution level and at the transmission level to try to understand the benefits of flexibility when it comes to electric vehicle charging. This is the type of information that I would be interested in chatting with people in this room about when it comes to plug loads, when it comes to smart buildings, when it comes to aggregating the different loads in your buildings, if there are opportunities to take any of those loads that are flexible and make a dent in some of these challenges and just help, especially move off the peak periods, whatever time that might be. So that's where I think the building loads come into play as being especially interesting, because there isn't sort of this bimodal time necessarily. We might be able to think about some of these periods where it's hard for EVs to shift. Maybe they're not even in the load profile at that time, but if there are opportunities for plug loads, it could be of a huge benefit to the power system planner and operator. So I'll just say again, all of our resources have been published. They're all publicly available. If you can't find anything and you'd like it, I'm happy to share it. This includes equipment stock, equipment sales, electricity demand, energy demand more broadly on an hourly basis for every state from today through 2050. Very high technology resolution. So even though I said we take all of the plug loads and we put them into another category, the base model itself didn't do that. We do have all the equipment broken out in a fair amount of detail, including televisions, dishwashers, washing machines, all the building loads, for example. So if there's interest in looking at sort of projections for those loads, not heavy variation on our electrification scenarios, just because they're all tend to be electric in nature anyway, but how they relate to the other electric loads, for example, under different levels of electrification, that's all available on our website and published in a variety of studies. The last thing I wanted to highlight is just that we also took all that information and we put it into our slope planning tool, or slope scenario planner. This is another public resource that's really designed to help state and local communities plan for an energy transition. So the goal is to take these national scale studies, which have sort of unimaginable numbers in them, right? Hundreds of millions of EVs. If I'm a state or local planner, I don't know what it means to plan for 500 million EVs. I want to know how many I'm planning for in my local community, for example. So we developed this planner to take our national scale studies and report it at a more local level. So that includes county level information for some of the data that we produce in our study, state level resolution for everything that we produce in our study. And we've made it available in this tool. I'll just skip over this piece. That basically walks through this, busy, I would say, not complicated, but busy workflow of taking the EFS results, layering it with more high resolution information, and then ultimately reporting 25 unique scenario strategy combinations that look at how impactful would electrifying all the vehicles in my county be? How impactful would it be to decarbonize my grid if I do nothing else with my building stock or with my vehicles, for example? What happens when I put those two things together? What happens when I layer energy efficiency of buildings on top of it? So adopting some of the codes and standards that we talked about earlier today in the presentation. Again, not as strong of a representation from industry in this case, just because we didn't identify really strong opportunities when we were performing our study, but ultimately trying to report especially the building and vehicle level data at a county resolution. So just a quick snapshot of what the control panel looks like, if you will. You search for the county that you want to look at. You pick the energy system metric that you're interested in, if it's energy consumption, emissions, or system costs. You can choose your grid evolution scenario, so business as usual, or we're pushing for 100% decarbonization by 2050, for example, and then layer that with different levels of efficiency, electrification, one additional level of efficiency, and then also increasing levels of flexibility of those electric loads in particular. And what it'll spit out is a chart of whatever you have picked, but it'll also put out these planning metrics. And this is another area I'd be really interested in people's perspectives on here at the lunch break or later today. Our planning metrics, again, really focus on those big categories. It focuses on how much of your how many EVs are in your system, what share of heating services is provided by electricity. Based on the talks earlier today, I'd be really interested if there would be value in adding how much of your load is actually from the other category that we have lumped together and we haven't zoomed in on at all. Do you need to understand that more to really capture the fact that we can't just plan for these big categories? We should also be planning for some of these smaller categories when you look at the whole stack, but potentially really impactful categories. So maybe adding a planning metric, if you will, on plug loads, for example, if we were to look at different scenarios of that level. This is an example of a chart that would come out, this one at a state level, but it really compares the cost of the higher upfront cost of electric technology with the reduced operating cost of that technology, and just showing the system planner perspective of, even if it's harder now, when you look at it over time and when you look at it with all the different categories accounted for, there are system cost benefits associated with electrification if you're driving for a decarbonized future. So that's everything I had. Happy to take questions, or I'll be here at lunch too if people want to chat one-on-one instead. Thank you.
Thank you very much, Caitlin. Very, very interesting work. Just curious, you mentioned you wanted to have a conversation with maybe people in the room here. And I guess I interpreted that as on the flexibility side, perhaps as one of the areas. But on that point, I wanted to ask you. You mentioned electric vehicles as one potential good source of flexibility. Did you do any meta-analysis or big analysis like that on all the loads that you analyzed, or just some anecdotal ones? And is that also available? And is that what you're trying to refine with these sort of engagements?
Yeah, I think meta-analysis would probably be a little generous. We did consider all of the bigger categories of load that are large enough as sort of a chunk to define the decisions on the bulk power system investment side of things. So ultimately that ended up being vehicles, space heating, space cooling as well, water heating. We actually we have cooking in there and dishwashers in there and things like that. So anything that was sort of a big enough wedge when we stacked up all the loads in a building especially, and then also light duty vehicles. And then what we did was review the existing incentive and demand response programs that exist. So our definition of flexibility for this modeling is just shifting load. We didn't have any shedding load opportunities, for example. We assumed that the same service demand applied. You could just move it in time, and how much you could move it in time depended on what your end use load was. So all that information is available. We do have, basically we have a sort of a static load shape and then a flexible load shape on top of that. And when we do our modeling, we let that flexible load shape be moved in time so that if the power system planner sees benefit in, if I could get all that off of my peak period, I don't have to build this resource anymore. Now this is what my load shape looks like. Can I meet that with my other resources? So that's part of the optimization problem that we have is allowing the operator to decide whether that makes sense. We didn't have any implementation or enablement costs included in that, so it's a free resource. So the bulk planner always wants to take advantage of that. But we did try to bound the problem by saying EVs can only be shifted by this much, air conditioning can only be shifted by 1 hour, pre-cooling or post-cooling, but no farther than that because customers don't usually allow for that. So the meta-analysis, which I think, again, would be a generous term, did feed into this definition of flexible load profiles, and it's mostly based on existing programs today, with the most aggressive ones being here in California. And when we look at really enhanced flexibility, what we tend to do is take the California programs and extrapolate them into the other markets of the region, and that obviously makes a much bigger impact at that point.
Caitlin, once again, yeah, great presentation. Just to follow up on your last statement here, I have several questions on each one of them, but I'll just ask three. The first question is the last statement that you made, taking California example. Are you following the example that's already happening in California through two programs? One, the CalFuse Vision from the California Public Utility Commission, and second is the Load Management Standards, or MIDAS, that the California Energy Commission is developing. There's a big move here, for flexibility especially on the electric transportation side, based on these two activities. Have you put that into any of your modeling framework that you're doing?
I don't think it would show up in this study because we did finalize these results about 3 years ago, 2 or 3 years ago. But we do have an active partnership with Lawrence Berkeley National Laboratory. They're tracking a lot of the flexibility programs in California and with the CEC. So we have some ongoing work to try to implement those measures in our modeling, but it wouldn't show up in detail in this study.
Yeah, I would recommend, in addition to that, you look at what the utility right here, Southern California Edison, is doing. They have a dynamic rate pilot now called the CalFuse pilot. It's all over in their emerging technologies for demand response, and they're actively working on projects, on field demonstration projects, including in the near future on electric vehicles. Okay, using the CalFuse framework. Question one. The second one is one of the charts that you showed on winter peaking versus summer peaking. Okay, is that are you talking about the coincidental peaking with respect to the peaking from electric utilities in that particular region, or is it just the peaking due to the increase in electric power for heat pumps only?
No, this is for all electricity demands in those regions. So for some things that have a really flat load, they'll show up in all hours of the year. What tends to be highlighted here and what tends to make the peak period, so define the size of the pie, tends to be the electric heating, but all loads in a given state are included in this calculation. The coincident peak is what's being presented.
Okay. That's important for utilities, obviously.
Yep.
It's the coincidental peak.
Yep.
The third question is on one of the charts that you had. How much is electrified in transportation? I mean, the rectangular thing that you showed.
Here.
Yeah. Have you kind of socialized this with the gas industry? Because I know we see a lot of presentations from the gas industry. Take, for example, GTI. I don't believe it shows the chart exactly like this, because there's a big push from that industry, obviously. And UC Irvine is working on some projects, focusing on the use of hydrogen and the use of, combination fuel, not only in the industrial sector, but in residential and commercial sectors.
Right. Yeah, I mean, we have not specifically approached that industry with this chart. This is just a historical chart of energy consumption by end use. So the opportunity is really just these arrows that are coming up. So bottom half here, these are all electric already. These are anything that's not electric. And then the opportunity just ends up being the arrows. But we did exclude, I think their comment would probably be, we don't think that there is as much opportunity in space heating, for example, as you think there is. But we didn't also assume that we electrify all space heating either. So we have had plenty of conversations with that industry about how realistic it is to assume we can electrify all heating, for example, in Southern California. And we would probably argue from an economic perspective it is. That's our economics, though, not their economics. It's not feasible from their perspective and their industry to get rid of all residential natural gas demand, for example. We've had those conversations. But my guess is they wouldn't push back too hard on this chart just because it's a historical snapshot and we haven't actually said how much of any of those boxes on the top would be electrified.
Yeah, I think it'll be good to kind of socialize this with the gas. We are doing it. I'm from EPRI, and we are doing it with GTI. We have an initiative called Low Carbon Resources Initiative, or LCRI. That's what we are trying to do, is to come to terms with, what the future is going to look like. Because the vision from different groups are very, very different, to be honest. Okay, so to show charts, in the public domain, in terms of how the future would be, they'll be good to have some sort of a reference on where it comes from. So thank you very much.
Agreed. I think there's a question.
Last question before lunch.
Thanks for the presentation. This is a question that I've asked myself, and it's probably a little bit unfair. Maybe we can talk about it over lunch. But I think it's sort of going forward with these analyses, I think it's sort of a categorical error to separate transportation from building loads, because all of these electric vehicles are going to charge at buildings. And which buildings they charge at has a lot of implication for some of the grid flexibility that you're talking about. And so I guess I'm wondering kind of how we unsilo this perspective of putting transportation as its own separate thing and start to think about where that charging is going to take place. And I think it's maybe relevant for this group because just by virtue of not being a water heating or an HVAC or a lighting load, those EV charging stations sort of become plug and process loads. And so I don't know if that's something that Calplug is thinking of incorporating into their vision, but I think it's a huge opportunity, obviously, for demand flexibility.
Yep, that's a great point, and I totally agree. I think it's somewhat arbitrary, the label we put on it at the end of the day in our modeling, because we don't represent individual buildings, for example. It's all load from a node, for example. And so we labeled it transportation, but we had the same debate actually about, is there effectively a separate transportation load? Because if it's happening, we're almost exclusively assuming either home charging or workplace charging. And in that case, those are both buildings. If you do have, a gas station, that would be a totally separate thing, a gas station. Right. So it's somewhat of an arbitrary label just because of how aggregate this modeling is. But to your point, when it comes down to your distribution level planning, where it is matters, and that will ultimately be at a building, that will ultimately be at a given substation, and you're going to need to plan for all of those things. So point well taken, and yeah, a connection that I didn't think of, but I agree with in terms of the collaboration between Calplug and this type of work.
Thank you.
Thank you.